Welcome to week 3 of computational algebraic topology, where we step away from the topology to focus a little bit more on the other two words in the title, namely computation and algebra. Let me tell you why we're doing this. The reason we're doing this is that despite all of our efforts in the previous week, all the tools that we built, carriers, NURBs, fibers, there is no precise algorithm that'll take in two simplicial complexes and tell you yes or no whether they're homotopy equivalent to each other. And so what we're looking for are homotopy-invariants for simplicial complexes. What that means is you want to take every simplicial complex, K, and assign to it some algebraic object, I of K. Of course, you can do this randomly, but that's not the point. The point is, if K and L are homotopy equivalent, then I of K is isomorphic to I of L. Okay, there's tons of stupid ways of doing this. I could take every simplicial complex and assign to it the number 0, and then if two simplicial complexes are homotopy equivalent, then, well, look at that. They both get the number 0, which is equal. The point is to find a good invariant, and this is a bit of an art form. What you need from a good invariant are, well, computability would be nice. We haven't really been able to compute anything yet. So machine computable invariants. And the other thing you'd like is that it's discriminative, not like the 0 invariant, which sends everything to the single number. If two simplicial complexes are different, ideally, I would give it different values to the extent possible. So let me show you the simplest homotopy invariant that is actually sort of interesting. So here it is. The Euler characteristic, EULER, Euler characteristic of a simplicial complex K is the integer chi of K in Z, defined as, so chi of K is going to be a sum over I going from 0 to the dimension of K of -1 to the I, so it's going to be an alternating sum of the cardinality of the number of simplices in K of dimension I. So you can play around with this a fair bit. I mean, this is really, really, really easy to compute. So what is the Euler characteristic of the solid 0 simplex? Well, there's just one thing in dimension 0, so that had better be a 1. Maybe we can be a little bit fancier. What about the hollow 2 simplex? Well, if you think about it, there's 3 vertices, so that gives you a +3. There are 3 edges, that's a -3, so that's a 0 when you add them up. If you choose to fill it in and get the solid 2 simplex, then you had a 0, you added a simplex of even dimension, so you get 1. And this game can go on and on and on. You can keep seeing new Euler, you can keep seeing new simplicial complexes and just numerically add the simplices and weight them by their dimension. So odd ones are negative and even ones are positive, and you add them all up, and there you go, you get the Euler characteristic. This is a remarkably simple looking object. It reduces an entire giant simplicial complex to a single integer. But here's the surprising part. Proposition, chi is a homotopy invariant. So if K and L are homotopy equivalent, then chi of k equals chi of L. And if you combine this with the example of the Euler characteristic of a point, which I'll highlight here, it's called a star. So star implies that every contractible simplicial complex K has chi of K equal to 1. So that explains the third calculation we did. We know that solid simplices are contractible, so that had to be 1 if you believe the proposition. I'm not going to give you a proof of the proposition. In fact, there is no simple proof of this proposition. To prove this proposition, you have to build an entire algebraic machine, which is going to be the subject of this week's lectures. So let's punt on the proof of this proposition for now, and instead, I'd like to show you my favorite consequence of Euler characteristic computations. So you might think this is a really ridiculous, simple, easily computable invariant. Who would ever care about something like this? So here is the most important Euler characteristic computation in the world. I learned about this from a paper of Anders Björner in 2011 called A Cell Complex in Number Theory. And here is how an Euler characteristic computation can be essentially impossible or really hard, depending on what you believe. Okay, so here's the setup. Let S be the subset of the natural numbers that is square-free. So square-free natural numbers. And to make life interesting, let's say they're bigger than or equal to 2. Square-free means they're not divisible. So n and n, such that no square of a prime divides n. So yeah, it's not hard to figure out what the first few terms of S should be, right? So 2 is definitely there. 3, these are both primes, so there's no way they're divisible by prime squares. 4 is not, because it's equal to 2 squared. 5 is prime. 6 is 3 times 2, no squares there. 7 is prime. 8, nope, can't have 8 because it's divisible by 2 squared. 9, can we have 9? No, it's exactly equal to 3 squared. Okay, you get the idea. So we're going to build a family of simplicial complexes with these numbers in S as vertices. So for all n bigger than or equal to 2, let Kn be the simplicial complex on the vertex set Vn. So this is going to get larger and larger as n gets larger and larger. So the vertices that are available to you are all the numbers in S which are less than or equal to n. And a K-simplex in the simplicial complex Kn is a list. S0 divides S1 divides S2 all the way up to Sk subset of Vn. So to get a K-simplex in this simplicial complex Kn, you need K square-free integers so that each one divides the next one. It's not too difficult to start drawing pictures of what this looks like. So V2 is just going to be 2. V3 is just going to be 3. V4 is the same as this. So V2 is just the single vertex 2. V3 is the vertices 2 and 3. V4, there's nothing happened. V5, you add this. V6 is interesting because you get 6, but now 2 divides 6, and 3 divides 6. So now K6 is, somewhat interesting simplicial complex, and you can keep going larger and larger. And at each end, you can evaluate the Euler characteristic, right? So here, the Euler characteristic, if you look, it's 3 vertices and 2 edges. So I guess the Euler characteristic is 1, maybe 2, 4 vertices and 2 edges. Okay, Euler characteristic 2. Anyway, so here's the main theorem of Bjorner's paper. If the growth rate chi kn as a function of n is no more than big O of n to the 1/2 plus epsilon for all epsilon bigger than 0, then we have the Riemann hypothesis, one of the most famous unsolved problems in mathematics. I think there's $1 million prize if you solve it. So just because the Euler characteristic is simple and easy looking does not mean that computing Euler characteristics won't make you $1 million.